Okay, Introduction to Statistics, Chapter 4, Describing the Relation Between Two Variables, Section 4.1, Scatter Diagrams and Correlation. Scatter diagram. The response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. You can think of the response variable as the y and the explanatory as the x from algebra. A scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis and the response variable is plotted on the vertical axis. A sample of a scatter diagram. If I gave you the points x1, y1. x1 would be the explanatory variable, y1 would be the response variable. And this would be the scatter diagram. If you look at the first point, 10, 8.4, you'd go across the horizontal axis till 10 and up the vertical axis to 8.04, and where those two meet would be that point. Another example is 13, 7.58. This would be this point, and you just plot all the points, and the scatter diagram is just a set of points. One of our goals will be to determine if the scatter diagram implies a linear relation, a nonlinear relation, or no relation. A linear relation occurs if the points on the scatter diagram seem to follow a straight line path. Two variables that are linearly related are positively associated if the response variable is increasing as the explanatory variable increases. The two variables that are linearly related are negatively associated if the response variable is decreasing as the explanatory variable increases. Now, an example of a positive linear relation. If you look at this set of points, okay, they look to follow a line. They're not exactly on the line, but they look to follow a line, and they're increasing from left to right. So this would be an example of a positive linear relation. If I drew a line in there, they somewhat follow that line. And later on in section 4.2, we'll come up with the equation of the line that best fits the data points. Now, a negative linear relation. Here's an example. If you look at this set of points, they're not quite as close to a line as the first set, but they do follow a set, but as you go on to the right, they decrease. So this is a negative linear relation. If you could draw a line, the line might be somewhere down through here that they would follow. Now, no relation. This is an example of no relation. It's just a glob of points. They don't look to follow a line. They don't look to follow any type of distribution. And then we have this set of points, which would be a nonlinear relation. They do seem to follow a pattern. They seem to follow the pattern of a parabola. Okay, so this would be nonlinear, but there is a relation. And now in this chapter, we're only going to talk about linear relations. Okay, the linear correlation coefficient, or Pearson product moment correlation coefficient, is a measure of the strength and direction of the linear relation between two quantitative variables. The Greek letter rho represents the population correlation coefficient, and R represents a sample correlation coefficient. In this chapter, we're only going to deal with the sample correlation coefficient. And as we go on in StatCrunch, they use a capital R instead of a lowercase r, but traditionally a lowercase r is what we use. Properties of a linear correlation coefficient. First, the linear correlation coefficient is always between -1 and +1 inclusive. That is, R is greater than or equal to -1, less than or equal to +1. If R equals +1, then a perfect positive linear correlation exists between the two variables. Every point lies on the line. An example would be here. If you have this set of points, you drew a line, every point is on the line. This would be a positive linear correlation. It increases as you go from left to right, and all points are on the line. Now, if R equals -1, then a perfect negative linear correlation exists between the two variables. And again, every point lies on the line. So here would be an example of a perfect negative linear correlation. The closer R is to positive 1, the stronger is the evidence of a positive association between the two variables. The closer R is to negative 1, the stronger is the evidence of a negative association between the two variables. If R is close to 0, then little or no evidence exists of a linear relation between the two variables. The linear correlation coefficient is unitless measure of associations, so the unit of measure for x and y play no role in the interpretation of R. The correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. We talked about this in chapter 3 with the mean and median. The mean was not resistant, the median was resistant. So correlation coefficient is not resistant. An outlier will affect it drastically. Now, finding the linear correlation coefficient and scatter plot for a set of data using StatCrunch. Well, we're going to load the data into StatCrunch, clicking the icon in the upper right corner of the data and choose Open in StatCrunch. Now we're going to select Stat on the top menu, highlight Regression this time, and select Simple Linear. Under the X variable, choose the column containing the explanatory variable. Under Y variable, choose the column containing the response variable. Click Compute. Now, once you click Compute, this would be your sample output. Okay? If we look at this output, there's a lot of information on it. We're just going to use some of it at this point. In section 4.2, we'll use other information from this. So first off, the linear correlation coefficient is R, right here. It gives you the R correlation coefficient equals negative 0.9578186, and you would round it to the appropriate places they ask for. But this is where the linear correlation coefficient shows up in this screen. Now, for the scatter plot, down here at the bottom, you will see a little arrow to the right. If you click this arrow, you will see the scatter plot. So if I click the arrow, this would show up. Now this is the scatter plot along with a line on it. Now if I wanted to go back to the previous screen, down here at the bottom, I click the back arrow. Go back and we're back where we started. Okay, so this is how we're going to use StatCrunch to find the correlation coefficient and the scatter plot. Testing for a linear correlation. Just because StatCrunch gives you a linear correlation doesn't mean one exists. We need to test it. First, you're going to find the linear correlation coefficient. Second, you're going to find a critical value in critical value table 2 for a sample size. Now, this table will be in the problems where you need to use it. You would click to open it. The table looks like this. On the left side is your sample size. On the right side is your critical value. If the absolute value of the correlation coefficient is greater than the critical value, we say a linear relation exists between the two variables. Otherwise, no linear relation exists. Okay, another way to think about determining if a linear correlation exists is by using the following illustration and interpretation. If you have a straight line, 0 in the middle, you'd have your positive critical value to the right and negative critical value to the left. Anything between those two values would be no linear relation or association. Now, if the correlation coefficient is positive and greater than the critical value, there is a positive linear association between the variables. If the correlation coefficient is negative and less than the opposite of the critical value, there is a negative linear association between the two variables. So a linear association occurs on the outside of the line. Now, an example. If n equals 7 and r equals 0.8125, is there a linear relation between the variables? Well, first, I know n, I know the correlation coefficient. So I go to my table. N is 7, so I find 7 in the table. So my critical value is 0.754. The absolute value of 0.8125 is greater than 0.754. Hence, a linear relation exists. Since 0.8125 is positive, we can say we have a positive linear association between the variables. Example 2. If n equals 10, r equals negative 0.7125. Is there a linear relation between the variables? Go to your table. This time n is 10. So our critical value is 0.632. If I take the absolute value of negative 0.7125, it is greater than 0.632. Hence, a linear relation exists. Since negative 0.7125 is negative, we can say we have a negative linear association between the variables. Example 3, if n is 5, r is 0.7895, is there a linear relation between the variables? Go to your table, n is 5, so our critical value is 0.878. In this case, the absolute value of 0.7895 is less than 0.878. Hence, no linear relation exists. So there's 3 examples where you get a positive linear relation, a negative linear relation, and no linear relation using the table. Now, we will now look at examples using StatCrunch to find the linear correlation coefficient scatter diagram and determine if a linear correlation exists. All right, looking at questions in StatCrunch. Okay, the accompanying data represent the total compensation for 12 randomly selected chief executive officers and the company's stock performance in a recent year. Complete parts A through D below. Okay, question A. One would think that higher stock return would lead to higher compensation. Based on this, what would likely be the explanatory variable? Well, you're trying to show that higher stock return leads to higher compensation. So you're going to start with stock return as your explanatory and show that it's higher compensation. Now it says draw a scatter diagram below for B. So we're going to open up our data. Now we're going to load the data in StatCrunch. So we click the icon, open in StatCrunch. Now I'm going to pin this to the right side, and then I'm going to go to the question and pin it to the left side. And I'm going to close my data set. All right, now we have 4 scatter plots here. If we look at the scatter plots carefully, we chose stock return as explanatory. So stock return should be on the horizontal axis. So that throws out A right away, puts B in, C out, D in. So it's either going to be B or D. Now let's use StatCrunch to create a scatter plot. So we hit Stat, Regression, Simple Linear, choose your stock return as your X, choose your compensation as your Y. Click Compute. This gives you the data. Use the arrow key to get your scatter plot. So here's our scatter plot. All right, now, just looking at this closely, okay, if I look here at B, I'm going to look at this first point right here. Okay, and this first point right here, and this first point over here. Which one does it look like? Well, it looks like it's going to be the B, not the D, because it's just over 2 lines. You know, it's between 10 and 15, and this would be 5, 10, this would be 15. This looks closer to 15. So if I open this up, take a closer look, you know, this looks very much like what we have over here. So it's going to be B. So that's more of a visual when you're doing the scatter plots. Now determine the linear correlation coefficient. Now I'm going to hit the back arrow to go back to my data. If you recall, the linear correlation coefficient was the R value right here. This is the R value. So the R value would be, and it says 3 decimal places. So I click over here, it's going to be negative 0.027 when I round it to 3 decimal places. Okay. So now I go down. Does a linear relation exist between compensation and stock return? Does stock performance appear to play a role in determining compensation of CEO? the linear coefficient is close to, well, it's close to 0. So no linear relation exists between compensation and stock return. It appears that stock performance plays no role in, no role in determining compensation. Okay? So that's the first type of question you might be asked. Now, a second question. Would be, Lyme disease is an inflammatory disease that results in a skin rash and flu-like symptoms. It is transmitted through the bite of an infected deer tick. The following data represent the number of reported cases of Lyme disease and the number of drowning deaths for a rural community. Complete parts A through C below. Okay, first, A, draw a scatter diagram of the data. Let the number of reported cases of Lyme disease be the explanatory variable. Choose the correct graph below. So now we're going to open up the Lyme disease table. We're going to icon, open in StatCrunch. I get a new StatCrunch window. Click at the top. Window right arrow to move it to the right. Close my data over here. Go under Stat, Regression, Simple Linear. Now it said Lyme disease was the X variable, explanatory. Drowning deaths was Y. Click Compute. Now I go to my scatter plot by hitting the right arrow. Here's my scatter plot. So I got to decide which one. Well, I can rule out D right away, right? Now let's see. Is it going to be A, B, or C? Just looking, can't really tell, except for I can throw out B because of these points up here probably. And I can probably throw out A because of this point up here. So it looks like it's going to be C. And like I said, this is more of a visual. And if you wanted to, you could have expanded this. And yes, this looks very similar to what we have. All right, D, determine the linear correlation coefficient. So I go back, hit the back arrow. Linear correlation coefficient is right here, which is 0.962. And they wanted 3 decimal places. So it's 0.692. Now C, does the linear relation exist between the number of reported cases of Lyme disease and the number of drowning deaths? Do you believe that an increase of Lyme disease causes an increase in drowning deaths? What is likely lurking variable between cases of Lyme disease and drowning deaths? Because the correlation coefficient is positive, it was positive. And the absolute value of the correlation coefficient is, well, if you take the absolute value, you get 0. Wait a second. I got the wrong one up here. This is 962, 0.962. So down here, the absolute value is 0.962. Is greater than the critical value. Well, I don't know. Let me go up here, view the critical value. So if I go under my critical value tables, over here, the sample size was 12. I can get it here, or I can look over here. So up here, sample size is 12, so I go down the chart to 12. Critical value is 0.576. Well, the absolute value is definitely greater than that. So it's greater than the critical value for this data set. Now they want to know what that critical value was. So I go back to the table. It was 0.576. And then a positive, since our correlation coefficient was positive, there's a positive linear relation. Okay? Now, do you believe that an increase in Lyme disease causes an increase in drowning deaths? What is the likely lurking variable between causes of Lyme disease and drowning deaths? Well, let's think about it. Do you think Lyme disease is going to cause a lot more drownings if the increase goes up? Well, probably not. Let's see what kind of lurking variables we have. Well, in A, an increase in Lyme disease does not cause an increase in drowning deaths. The temperature and time of year are likely lurking variables. An increase in Lyme disease does not cause an increase in drowning deaths. Well, there are no lurking variables. If there were no lurking variables, we are showing an increase in drowning deaths. An increase in Lyme disease does not cause an increase in drowning deaths. Pesticide control and lifeguards are likely lurking variables. I don't know what pesticides has to do with drowning. An increase in Lyme disease causes an increase in drowning deaths. There are no lurking variables. Well, like I said, I'm not so sure Lyme disease causes drowning. So let's go back to A. Does temperature and time of year, are they likely lurking variables? Well, yeah. If it's very cold outside and the time of year, if somebody falls in, the water in January, they're more likely to drown than if they fall in the water in July or June. So I think temperature and time of year would be your likely lurking variables. So that would be A. Okay? Now, going on to a third question. Use the data to complete parts A through B below. So again, draw a scatter plot. So I'm going to open in StatCrunch. So I hit Stat, Regression, Simple Linear, and I forgot to shift this over, so let me shift it over. And my X variable is going to be X, my Y variable is going to be Y. Click Compute. Click the arrow at the bottom to get my scatter plot. So this is what my scatter plot looks like. So which one of these is it? Well, I can't really tell looking at them. So this is going to be one, the numbers are small enough. So I'm going to look at the chart. 2.2. 2.2 was 3.9. Well, 2.2 is right about here, and I don't see any point above it, right? And 2.2 is here. Oh, that looks like 3.9, so that's good. 2.2, that looks like, no wait, that looks higher than 3.9. That's 4.9, isn't it? So over here, 2.2, that looks like 3.9. 2.2, no. So just using that first point, it's going to be C. So this is more of an understanding what a scatter plot is. Now, compute the linear correlation coefficient. The linear correlation coefficient for the four pieces of the data is, so I go over here, hit the back arrow. My linear correlation coefficient is 0.73, 3 decimal places, right? So this is 0.073. And now, draw a scatter diagram of the data with additional data point 10593. Choose the correct answer below. So now what I'm going to do is I'm going to go over to my data set. They're asking me to add another point. So I'm going to click here below the 4.8. I'm going to add 10.5. And then below in the Y column, I'm going to add 9.3. Okay, now I'm going to go back, do the same thing I did before. Regression, simple linear, X, Y, click compute. Click the arrow to see the scatter plot. Now here's the new scatter plot. Okay. Now they want to know which one of these below would be. Well, once again, we can look at 2.2, right? Well, now these on the x-axis are going by 2's. So if I'm going by 2's, right here is 2.2, and I need 3.9, so that looks good. 2.2, there's no point there. 2.2, no point there. 2.2, the point is way up here. So it looks like it's going to be A. Okay? So that's just by looking at the data and finding the correct point. Now, compute the linear correlation coefficient with the additional point. So I go back. This time the linear correlation is 0.866. Comment on the effect the additional data point has on the linear correlation coefficient. Well, before I had 0.073, now I have 0.866, much stronger linear correlation coefficient, closer to 1. The additional data point does not affect the linear correlation coefficient. Well, it did. It made it go a lot larger. The additional data point strengthens the appearance of the linear association between the data points. The additional data point weakens the appearance. Well, we went from 0.073 to 0.866. That definitely strengthened it. So that would be B. Explain why correlation should always be reported with scatter diagrams. The scatter diagram is needed to determine if the correlation is positive or negative. The scatter diagram can be used to distinguish between association and causation. The scatter diagram is needed to see if the correlation coefficient is being affected by presence of outliers. Okay, that's what the scatter plot really does. Scatter diagram shows us if there's any outliers. Okay, now we go to a fourth question. Suppose the two variables x and y are negatively associated. Does this mean that above average values of x will always be associated with above average values of y? Explain. Well, if we look at a scatter, let me go over here to the last scatter plot. You notice some of the points are above the line, some are below the line. Okay, so these would be above the average, this would be below. So we can't really tell whether it's going to be above or below. So in this case, so does it mean the average above x values will always be above or below? No. So it's going to be a no answer. Now I got to figure out which no, because there will always be at least one point that does not fit the trend. No, because when two variables x and y are negatively associated, above average values of x are associated with above average of values of y. So that's not it. No, because association does not mean that every point fits the trend. The negative association only means that above average values of x are generally associated with below average values of y. Let's read this again. Association does not mean that every point fits the trend. The negative association only means that above average values of x are generally associated with below average values of y. Now it just says because of the word generally here, so it's going to be D. So you have to read the questions very carefully. Alright, so that takes us through some examples for Chapter 4, Section 4.1.